Hello, Astro students. How about a little help with escape velocity so you guys can do your homework? So let's have an Earth. And on this Earth, we're going to have a spaceship. And in that spaceship is Newland, who wants to escape and go somewhere else and be happy. Actually, I'm happy here. And there are my three little engines. But at first, I'm one Earth radius from the center of the Earth. And the equation that I'm not going to derive for you here because this is not a physics class, for gravitational potential energy. So this is gravitational potential energy, which I need to overcome. Another way of saying that is kind of like the gravitational well of the Earth. That's negative big G, mass of the Earth, which is what I want to escape, mass of my spaceship, which is what I'm trying to get off the Earth, divided by the radius of the Earth. And that quantity is negative for a reason. And then later on, after I fire my engines, there's my Earth again. Here's my spaceship now, partially in the air. There's my little window with me being happy in there. And so now my little engines are firing again, or not again, but still. And I'm still going to need to know how far from the center of the Earth I am. In fact, now I'm a little bit farther away. So R sub E plus how high I am. Now we don't do that. Forget that. We're close enough to the surface that we're still one radius away. Don't worry about that. And we've got some speed now that I'm going to call escape. That what I'm trying to do is get going fast enough that that I want to cancel out all of this UG. By the way, this is called kinetic energy, or kinetic energy is also known as energy of motion, and that equation is 1/2 m spaceship v escape squared. So that says the mass of the thing that's moving times the speed that it's moving squared multiplied by half. That's the energy of motion. The energy of gravity just existing up here is big negative big G MEMS over RE. And what I'm saying is that I want, you can escape when the two of them added together is 0. Now, in reality, what that means is it would take infinitely long. T would have to go to infinity. So what you really want is K to be, so we don't want to wait that long. No one wants to wait that long. Like wait infinitely long to leave. What you really need is for K to be greater than U. So in order to escape, and then you're happy. Look how happy you are. In order to escape, K needs to be greater than U. But for this derivation, let's figure out the minimum speed. Let's just say that K needs to be exactly equal. So let's just say that the sum of the two, that what I'm really saying is 0 is going to equal 1/2 m spaceship v escape squared minus big G MEMS over R sub E. But I know that I want the sum of them to be 0, so I can just take this thing and move it over to the other side. So really what I'm saying is the kinetic energy needs to be equal to the potential energy. And again, this will take infinitely long. So whatever that speed is I'm going to calculate, I'm going to turn the little dial on my engines up so I'm going faster than V escape. But what I'm trying to do right now is figure out exactly the minimum. So notice in this expression that even though it takes a lot of energy to get my spaceship moving, once I get it up to speed, the mass actually is not the problem. It can be hard to get my spaceship moving that fast. I have to fire my engines to get me moving that fast. But once I've taken care of that engineering problem, all I need to do is use the energy of motion, and the mass of my spaceship is actually not going to factor into this equation. So let's solve this now. So V escape squared is going to now equal 2G M Earth over, that's an E right there, R sub E. That's how far I am from the center of the Earth. So here, let's scroll down a little bit so we can solve this. So that really means that V escape is going to equal the square root of 2G ME over R sub E. But we can generalize this. This is the mass of big thing. We need to know how how much material the thing we want to escape contains, or its mass. And we need to know how far we are from center of big thing. So it doesn't necessarily have to be on the surface, even though generally if you're in a spaceship, you're on the surface you want to leave of something like the Earth or the Moon. Really what I'm saying is how far am I from the center of the big thing? So this equation can be generalized. The r on the bottom here could just be how far you are. It doesn't necessarily have to be the radius of the planet, even though that's often the case. And the big G right there is the same big G that we use for universal law of gravitation, assuming we're using kilograms, meters, and seconds. That's 6.67 times 10 to the negative 11th units. I don't remember the units off the top of my head. And that would make the mass in kilograms and the radius in meters. So be careful with that. And if you finish with all that, then units over here better be meters per second, assuming you use meters, kilograms, and seconds for everything on the right-hand side. Then on the left-hand side, you end up with units of meters per second. It is quite common in space exploration and in astrophysics to use kilometers per second. So be mindful of that when you're looking at UT homework problems. Make sure the units are right. But there's the equation. That's you could have looked it up, but I wanted to show you a derivation where it came from. So now you can actually do your homework.